We are now designing a controller, specifically a lead controller. It is in this configuration, the unity feedback configuration. We're given the Bode plot of this plant or this process without any controller in it. And from there, coming up with the parameters of a lead controller. What does a lead controller look like? It has this transfer function: gain, a 0, and a pole, where the pole is further to the left than the 0 in the complex plane. Here is the Bode plot of just the controller, which will add to the whole Bode plot of the forward path. We're going to add some amount of phase. The further apart we spread the pole and 0, the more phase we add, up to 90 degrees. So we can make it as big as we want, theoretically, up to 90 degrees. But the more we spread them apart, the more gain we add. So we don't want to add more gain than we have to. So let's find out how to go about this. First thing we're going to do, well, here's what a lead controller looks like. First thing we're going to do is rewrite it this way, so we separate this case of naught. This way, the case of naught can be selected separate from where you place the pole and 0. And you can base the case of naught on one of two specs, either a steady state error spec or a bandwidth spec. And then we would pick, and by the way, then this K is related to that case of naught by this factor of A, where A is the spread between the 0 and the pole. And then the other spec would be a phase margin spec, which would come from, say, a peak overshoot spec or a resonant peak in the frequency domain spec. And by how much extra phase we need, I won't go through this derivation, but we can calculate an A by how much extra phase or how much phase we need to add from the controller. So this phi sub m, this amount of phase will be somewhere between 0 and 90 degrees. If we had that phi sub m, we could calculate the A. So that's the general idea. Pick the case of naught based on a steady state error bandwidth spec, base the A, and where to place the P and Z, the pole and 0, based on a phase margin spec. Here's our example. This is the plant. Our specs are a steady state error to a ramp of 0.1. See that it's a type 1 system. The controller doesn't have any poles at the origin. So it doesn't change the type of the system. And our second spec is a peak overshoot spec of 25%. Here's what our controller is going to look like. Let's go through. Well, here's what the Bode plot of just uncompensated original plant looks like. And we said before how to interpret that. We could find the case of naught and what type it is and some other things from this. Phase margin, let's see, that would be about, just the gap, I guess a little over 45 degrees. Let's call it about 50 degrees. But our case of naught's about exactly 1. So we're not meeting our steady state error spec. Step 1 is to choose that case of naught. And this formula is derived in my notes on my website. The URL, the website is in the description of this video. I get this case of error by the steady state error spec. Since it's a type 1, this case of error will be case of V, and it is just 1 over what the error spec is. So error spec is 0.1, so case of V is 10. Our G sub naught, this G sub naught is the plant G, with its pole at the origin removed and the rest of it evaluated at 0. Remove this pole, evaluate the rest at 0. I just get 1 over 1 or 1. So in our case, G sub naught at 0 is 0. K sub error was 10. So my K sub naught needs to be 10. Here's the effect of step 1. Increase the gain by a factor of 10, which is 20 dB. So we move our reference line down. It is 20 dB below. This is the new 0 dB line, which so we meet our steady state error spec. We have a new crossover frequency. It used to be back here at about, I don't know, 7 or 8. Now it's out here at about 3. So we changed the bandwidth. And we're going to get less phase margin because we're out here now. What's our crossover? It's about the crossover frequency here. We're more like, I don't know, 20, phase margin of 20 degrees. An optional thing to do is to redraw your Bode plot to include that new gain. So here's our new 0 dB line that corresponds to this reference line. And MATLAB could calculate that phase margin exactly. It's 18 degrees. And our crossover frequency exactly. So that's step 1. After that, we're going to use the phase margin spec. Now we'll find out where to place the pole in the 0 now that we've got the K sub naught. And I'll save that for a second video.